Okay, let's get started. I've got to spend the better part of one more lecture telling you about lattice vibrations. Again, this is stuff that it's just not possible to do without showing you a little bit of mathematics. You're not going to be examined in any depth on this mathematics, certainly not beyond the level of what you'll see in the homework. And so the really important thing is to understand qualitatively what we're talking about here. Remember, that, and this is very important, that when we considered the thermodynamics of equilibrium, that we recognized that the thermodynamics of equilibrium led us to consider a number of different thermodynamic potentials, each of which would govern equilibrium by an extremal principle, a minimum or a maximum. These different thermodynamic potentials are not different things. They are really different ways of saying the same thing. The difference between them is that they pertain to different experimental situations. When you are trying to analyze a situation that's going on in the laboratory, you begin by saying, what is it about this experiment? What parameters can I control? And what parameters do I get as a result of the parameters I control when equilibrium is achieved? If you are dealing with an isolated system, the parameters you can control are the energy in a fluid. The parameters you can control are the energy, the volume, and the chemical content, because you put those into the system before you isolate it. The equilibrium state of that system is then governed by the entropy maximum principle. The system is at equilibrium when the entropy takes on the highest value it can possibly have for those given values of EV and N. Another common situation is when you have a system that's inside a box of some sort, but it's in thermal contact with its environment. In that case, the variables you control are the volume, the chemical content, because you put those in the box before you sealed it, and you control the temperature. It's the temperature of the environment. In that case, the pertinent thermodynamic potential is called the Helmholtz free energy. It's the energy minus T times the entropy. It's a function of T, V, and N. And the condition of equilibrium is that the value of the Helmholtz free energy of the system, forget the environment, must have the least value it can have for given values of the number of variables that you control. Another common situation, in material science often the most common situation, is where you control the temperature, the pressure, and the chemical content. You just have a solid sitting in an atmosphere in a certain environment. In that case, the pertinent thermodynamic potential is the Gibbs free energy, E minus Ts plus PV, and the condition of equilibrium is that the Gibbs free energy of the system must have the lowest value it can have for given values of T, P, and N. The final situation, which is really much more common than thermodynamics text would lead you to believe, is the open system, where we just imagine a region of space. In that case, we control the volume because we've got to define the boundary that defines our system. But the temperature and the chemical potentials are then set by the environment through the conditions of equilibrium. In that case, the pertinent quantity is the so-called work function, omega, which is E minus Ts, I didn't put the full definition down here, E minus Ts minus the summation, chemical potential times mole number, which is also just minus PV, where P is the pressure and D is the volume. And that must be a minimum. Or equivalently, if you have an open system, the pressure must have the maximum value that it can have for given values of the temperature and the chemical potentials. Those are the global conditions of equilibrium. You know which one to apply in a particular situation by just asking yourself, what variables do I control and which ones don't I control? And the variables you control tell you what thermodynamic potential governs equilibrium. Okay, let's take a simple solid. The thermodynamics of simple solids, to first approximation, is really pretty simple because it's controlled actually by two parameters. One parameter is the energy at 0 Kelvin. If you just calculate the energy of the single component solid in its ground state at 0 Kelvin, that gives you this quantity E0. As the temperature is raised, the entropy of the ground state is 0 by the third law. As the temperature is raised, we get an increase in both the energy and the entropy because of thermal effects, and that increase in both cases is determined by the specific heat at given temperature. So if we know the specific heat, CV, the change in energy with temperature at constant volume, if we know that quantity as a function of temperature, then we can simply integrate, determine E, determine S, and therefore calculate the Helmholtz free energy. So the Helmholtz free energy, and this is a good free energy to use because the Gibbs free energy and the Helmholtz free energy for a simple solid are essentially the same, unless you impose enormous pressures. So this is all we need to know, and it's relatively easy to calculate, provided we know the specific heat and how it changes the temperature. Yeah.
So what is the Helmholtz energy represent? Like, is it like ability to do thermal work? Or
I'm sorry.
What does it represent? If I told you the Helmholtz energy is X, what does that mean?
The Helmholtz free energy turns out to be the maximum, I'm not going to prove it here, I'll just tell you, turns out to be the maximum amount of mechanical work you can do in a system at given temperature. That's why, if you're interested in how much power we can make in the United States, the issue is how much Helmholtz or Gibbs free energy is available for us to use. And it is the maximum work. But we don't need to know that, so I'm not going to talk further about that. But I'm going to talk about the specific heat. The specific heat of all solids is actually almost the same, or at least it has the same behavior. Down here at very low temperature, specific heat goes to 0 when temperature goes to 0. Down here at low temperature, it starts picking up roughly like T cubed. At high temperature, for every material in the whole wide world, the specific heat has exactly the same value, and that's 3 times N times K. 3N is just the total number of atoms in the system. So at high temperature, we know what the specific heat is. At low temperature, we kind of know how it varies and just kind of fares from low temperature to high temperature in a curve or something like this. The high temperature limit comes when the temperature exceeds a characteristic temperature known as the Debye temperature, theta D. Now that is a parameter that varies from material to material. So if you're interested in knowing the specific heat of the solid, so that you can calculate it for various different materials, it turns out the only parameter that strongly influences the specific heat is the Debye temperature. Other than differing Debye temperatures for different materials, this curve has pretty much the same shape, and without making too big an error, I can just find a Debye representation of this curve, which is well known, and use it for any solid. So the behavior of the free energy is really, the thermal behavior of the free energy is really rather simple. And it's governed by, to a good first approximation, is governed by a single parameter, which is the Debye temperature. Well, why? And where does the Debye temperature come from? There are two possible contributions to the thermal energy of the solid. As we go up in temperature, the atoms are going to vibrate, and they're going to vibrate more and more energetically as the temperature goes up. That's one source. Second thing that's going to happen is that the electrons are going to be able to move into excited states as we go up in temperature. That's the second source. The electronic specific heat, in almost all cases, is negligible compared to the vibrational specific heat. So to understand the specific heat and why that curve has the form it does, we've got to understand how the vibrations are contributing to the energy. And that, unfortunately, gets a little messy in both visualization and mathematics, but we want to understand it at least qualitatively. If you look at it just a solid in a crystal, every atom in the solid goes into thermal vibration. Every atom can vibrate in 3 directions. So if we have N atoms, we have a total of 3N degrees of freedom. Now in classical mechanics, which would pertain at high temperatures, each of these degrees of freedom would have an energy, a kT, associated with it. So the total vibrational energy at high temperature is 3N kT, giving us a specific heat, 3N K. That's this high temperature limit, and that holds for any material we want to talk about. So all of the complexity in the specific heat comes in the low temperature behavior, which determines the shape of the curve and also determines what that divide temperature is going to be. Well, we briefly discussed the vibrations of the atoms in a solid last time. You begin with a linear chain and you assume 1 degree of freedom, just transverse vibration. Then if you pluck one of these atoms, it will influence its neighbor, which will influence its neighbor, and so on, so that you will get a vibrational wave that will move down this chain and back in this chain and will give you a vibrational state. You end up, if the amplitude is not big, this vibration is sinusoidal, the wave has a sinusoidal shape. And however, the displacement is only defined, that is the amplitude of the wave, is only defined at the individual positions of the atoms. What the wave looks like in between these atoms, we have no way of knowing because there are no atoms there to vibrate. So we can describe the wave, the displacement at position x, which is a number, an integer number n multiplied by the interplanetary spacing a. Just give it a sinusoidal form, u0 exponent ikx, or u0 exponent ikna, since those are the only values x can have, where k is the wave number, 2 pi divided by the wavelength lambda. Here's half the wavelength right here. Lambda is the wavelength, 2 pi over lambda is the wave number, and a universal sinusoidal wave has a displacement described by u0 exponent ikna. In physics, we almost always assume periodic boundary conditions. By that I mean we don't want to worry about a free surface unless we're specifically concerned about free surfaces. So we imagine this chain, which has n atoms in it, is just repeated and repeated and repeated forever. And we set a periodic boundary condition by assuming that the displacement at the repeat of the chain, if there are n atoms in the chain repeats every distance n a, where a is the interatom separation. So I assume that u at x plus n a is equal to u of x. The only way this is going to be true if you plug back in this formula is if k times capital N times a, wave number times the number of atoms in the chain times displacement, is an integer times 2 pi. Because the exponent of I, 2 pi q, where q is an integer, is just equal to 1. So if this is true, this k and a adds the factor 1, and the displacement at x plus n a is exactly equal to the displacement at x. So that tells me that the values of k are discrete. The wave numbers must have discrete values. And those discrete values are 2 pi times q over na, where q is an integer. Well, it also turns out mathematically, if I just add the number n to q, I will repeat the same set of wave numbers. So it turns out that there are exactly n, capital N, wave numbers, which means that there are exactly capital N different waves. And those waves are in a range of k that I can do it in various ways. But it is very useful to make the values of k symmetric. So we'll take k from minus pi over a, which happens when k is minus n over 2, to plus pi over a when k is plus n over 2. And we let k have n discrete values that range from minus pi over a to plus pi over a. Now, the important thing about there being only n discrete values is that when you change the description of a vibration, the thing that doesn't change is the total number of degrees of freedom. If I have a certain number of degrees of freedom in one description, and I have another valid description, I'm going to have the same number of degrees of freedom. Going back up to this chain, if I just look at each atom individually, I only have 1 degree of freedom here, up and down, so each atom has 1 degree of freedom. So the total number of degrees of freedom is equal to capital N, which is the number of atoms in the chain. Well, now I have used a different description. Those of you who are familiar with Fourier transforms know that we can describe things in real functions of real space, and we take the Fourier transform and describe them in Fourier space. That's basically what's going on here. We are replacing the atoms by sinusoidal waves. If we had n atoms and therefore n degrees of freedom, if we describe it correctly, we're going to have exactly n sinusoidal waves. The number of sinusoidal waves will be equal to the number of atoms because the number of degrees of freedom is going to be the same. So we wind up with a description of this vibration which gives us capital N sinusoidal waves described by these n allowed values of the wave number ranging from minus pi over a to pi over a with q as an integer. Okay. Well, this kind of just really just iterates what I just said. Q minus n over 2 to n over 2, so they're n values, means k minus pi over a to pi over a, and that's what's called the first Brillouin zone of the lattice vibrations. The dispersion relation. The next thing we need to know, because the energy of a vibrational wave does not depend directly on its wavelength. The energy in quantum mechanics is h bar omega, it depends on its frequency. So to translate from waves from descriptions to energies, we have to find out how the frequency, angular frequency omega, relates to the wave number k. And you can kind of see how that's going to go by recognizing that the frequency of the wave is going to depend on the restoring force. If I pluck this string of atoms like here, the distance between this atom and its immediate neighbors has increased slightly. Because that distance has increased slightly, there's going to be a pull to pull that part of the wave back and restore it to its original configuration. The bigger the difference in displacement between adjacent atoms, the bigger that restoring force is going to be, and therefore the bigger the frequency is going to be. So the sharper the wave is, that is, the shorter the wavelength, the bigger the restoring force is going to be, the higher the frequency is going to be. Now, in three-dimensional problems, you'll get into some complications with that, but this is good enough for our purposes. But just look at that. When the wavelength is infinite, and I displace this row of atoms, it just displaces as a row of atoms. There's no increase in the displacement between adjacent atoms, so there's no restoring force. If I would imagine I could do this, because it's 10 to the n, so I couldn't. If I could imagine that I could do this and just displace this rigidly in this direction, there would be no restoring force at all. It would just keep going. So when k is equal to 0, lambda is equal to infinity, the frequency is 0. The wave will never come back. The minute I start putting in some sinusoidal character, however, I put in a relative displacement between adjacent atoms. So now there's a restoring force, and omega starts building up. And in fact, the shorter the wavelength, the bigger omega is going to be. Initially, when the wavelength is still very long, that means the wave number is very small, that restoring force will increase linearly with k. The frequency can be shown to increase linearly with k. Omega equals ck, and c is the sound speed of waves along this chain. We call it the sound speed because in solids, you whack something, you get a tone, that's a sound. The waves that cause that sound are waves you can hear, and the waves you can hear are very long wavelength waves in atomic terms. So the sound speed is the speed of long wavelength motions, and those are the ones here at k equals 0. As we get out toward the boundary of the Brillouin zone, however, we get into, in fact, just by symmetry, when the dispersion relation, omega versus k, hits the edge of the Brillouin zone, it must be horizontal at that point, because this function has to be symmetric if I continue it mathematically into the next zone. So it has to hit this boundary parallel, and therefore it has to bend over, something like I've shown here. And this is a typical form of a dispersion relation for a linear chain, simple linear chain. The highest frequency is usually right here at the boundary, and that's because when I hit the boundary, adjacent atoms are moving in opposite directions. I didn't draw it, but when I'm right out here at the boundary, if this atom is moving up, the one next to it is moving down, the one next to it is up, and so on. And that's the biggest relative displacement of adjacent atoms that I can possibly get. So that's what's happening in the linear chain. We then get a dispersion relation. And that gives us the angular frequency omega as a function of the wave number k. They're exactly n different waves of this type in this n chain. Well, the next sophistication is to recognize that I've only talked about one of the 3 degrees of freedom that an atom can have. This atom can move orthogonally up and down in the plane. It can move in and out of the plane. And it can also move longitudinally. That is, it can move in the direction of the atom next to it. That gives rise to a dispersion relation which has 3 branches. One describing the up transverse waves, one the out transverse waves. By symmetry in this linear chain, they have exactly the same properties. So I have a curve down here for transverse waves, which is degenerate. There are 2 sets of waves contained in this curve. And then I have here a curve for longitudinal waves, which is generally significantly higher, because when the atoms start moving toward each other, their distances change more rapidly with wavelength. So the longitudinal waves are slightly above. That's a sophistication we really don't have to worry about that much. The next sophistication are the optical modes. Still more complicated things happen when we have more than one atom in a unit cell. In a linear chain, that would be, for example, a 2-atom unit cell would be, say, a big atom and a little atom in adjacent positions here. Now we have 2 different sets of possible vibrations. They're the vibrations in which the 2 atoms in a unit cell move together. They're both displaced up. They're also the displacements in which the 2 atoms in the unit cell move in opposite directions. The displacements in which the unit cells move up or down are called the acoustic modes. Those are the low-frequency modes, and those look just like the dispersion relation or the modes for a linear chain of like atoms. However, the situation when the 2 atoms are moving in opposite directions looks rather different. Even when the wavelength is infinity, k equals 0, I'm still going to get a rather high frequency for these modes, because when these 2 atoms within the unit cell move in opposite directions, they displace from one another, and that gives me restored force. That gives rise to what I call the optical modes. So the total dispersion curve looks something like this. The optical modes become rather important. They're called optical modes because they can be very active in the optical properties of materials, and that's why I'm defining them here so that we can talk about them later. Other than that, I'm not going to talk about the optical modes. But what happens in 3 dimensions? Actually, in 3 dimensions, the description of waves in 3 dimensions is very, very similar to the description of waves in a linear chain. And the reason is that the waves that move through the solid in 3 dimensions can be described as plane waves, or written as plane waves. Now, in a plane wave, what happens is planes of atoms vibrate with respect to one another. And if I just look at a linear chain in which each atom in the linear chain is now plane, the qualitative characteristics of the vibration are going to be exactly the same. The only difference is that now I have lines of planes in all possible directions. So here the displacement is a vector displacement. The vector displacement of the atom located at point r is u0 exponent I, the vector. Now the waves are characterized by wave vectors, where the magnitude of the wave vector k is 2 pi over lambda, just as it was before. The direction of the wave vector k is the direction of wave propagation. The description in 3 dimensions is a little bit more complicated. You don't need it. I'm not going to give it to you. Take a solid-state physics course and learn about it if you're really interested. But it turns out that, just as we might expect, the total number of possible values of the wave numbers k, or the wave vectors k, is 3n, where n is the number of atoms contained in the solid. These 3n values are contained in the 3D Brillouin zone, which for a simple cubic solid would have a simple cubic shape like this. For a face-centered, body-centered cubic solid, it has a much more complicated shape. We don't have to worry about that, just accept that it does. You can actually get away with visualizing any section through it looking like this. So that's essentially what's happening in 3 dimensions. The dispersion relation is complicated, but the one-dimensional visualization of it will get you through most problems that you need to understand. All right, now we have to worry about the energy. Because if we're going to calculate the vibrational specific heat, we have to find the vibrational energy and differentiate that with respect to the temperature. So let's go. Our lattice vibrations are quantized. I have 3n vibrational modes in the solid. Each of those vibrational modes has a wave number k, wave vector k in 3 dimensions, and it has a frequency omega of k. The energy associated with the vibrations in that mode are this: n plus 1/2 h bar omega. H bar is Planck's constant over 2 pi. Since omega is 2 pi nu, where nu is frequency in cycles per second, this is just h nu. This n is telling me this is the level of excitation. Lattice vibrations are what we call in quantum mechanics bosons, which means I can have many, many particles, if you want, in the same state. And this n is just telling me the number of particles or phonons I have in this particular state with this frequency omega. The total energy associated with vibration in that particular mode is equal to the number of excitations plus 1/2, that's a 0-point vibration, times h bar omega. N is a function of t, the expected number of phonons. So what we need to know is n. We get omega as a function of k from the dispersion relation, so we need to know n. Well, since the phonons are bosons, they obey Bose-Einstein statistics, which I will not derive for you at this course. It can be derived. It is possible to prove that this is true. The number of phonons at a given value of absolute temperature is 1 over the exponent h bar omega over kt minus 1. This is the Bose-Einstein function. It's mathematically kind of complicated, but most of the time we don't care, because we look to its high and low temperature limits. Suppose we have a particular frequency omega that is of interest to us. And suppose our temperature is such that kT is much, much greater than h bar omega. The thermal energy is much, much greater than the vibrational energy. When this is true, you just plug into this equation, use the expansion to your exponent, 1 plus h bar omega over kt minus 1, and n of t turns out to be just kt divided by h bar omega. So when I'm at high temperature, and high temperature means that for the phonon I'm interested in, kT is much greater than h bar omega, the number of excitations is just take kT over h bar omega. When I'm at low temperature, when h bar omega is much, much greater than kT, for the